Hello, my name is Kyle Rose, and the title of this presentation is Pythagorean Theorem and Order Theory. This presentation will cover some of the research that I, Dr. Schwanke, and Zachary Ward have done. Instead of just jumping straight into the research, I thought it'd be interesting to take a look at the Greek mathematician himself, Pythagoras. Pythagoras was born in the 6th century BC and is known for many things, one being his philosophy, Pythagoreanism. Not gonna lie, it seems a bit cultish. Like they believed in beans being taboo and, drowning people to disprove core parts of philosophy. But the other thing that Pythagoras is most known for is his mathematics. Seen here is a high school geometry student's worst nightmare, the Pythagorean Theorem. This theorem simply states that if you have a right triangle, then the sum of the squares of the two shorter sides, A and B, is equal to the square of the longest side, C, or the hypotenuse. Now, there are a good amount of current day applications of the Pythagorean theorem, including construction, gardening, and navigation problems such like this one. Using the Pythagorean theorem, we can calculate the length of C Street using the lengths of A and B Street, which in this case C Street is 2.5 miles long. But what if there was another way to do this? To answer my rhetorical question, yes. We are able to prove that this long string of letters and curly braces is equivalent to the Pythagorean theorem. Now I won't be going over the proof we came up with, for it's way too long and complicated. Instead, I'll break this equation into easy to understand pieces, and then bring them all together at the end. To do this though, we must first talk about functions. Functions are like relationships. In a good relationship, when you put stuff in, you get something in return. If you don't get anything out of it, then it's a bad relationship, meaning it's not a function. There are many interesting things about functions, but for this presentation we're going to focus solely on order theory, or infimum and supremum of a function. We generally call the infimum the greatest lower bound, but we can also think of it as the absolute minimum, or the smallest number possible of a function. As an example, take this function here. The infimum, or absolute minimum, is 1, because with any number you plug in, the smallest number you get in return is 1. In addition, we have the supremum, or the least upper bound. We can think of this as the absolute maximum of a function. Looking at the examples, we can see that sometimes in supremum or infimum may be infinite, because no absolute maximum or minimum exists. The concept of infimum and supremum are important to us for two main reasons, one being something called the geometric mean. Now you may be familiar with the arithmetic mean of two numbers, A and B. Is where we add A and B and then divide by 2. However, the geometric mean of two numbers, A and B, is just the square root of A times B. What's really cool about this particular geometric mean is that it has been shown that this is equal to the infimum of the function f of x is equal to ax over 2 plus b over 2x. I don't have time for an extensive proof showing it's true, but how about a simple example as proof? In this example, we have the square root of 9, which is just 3. However, with slight manipulation, we can rewrite it as the square root of 3 times 3. Using the geometric mean, we get an infimum that when graphed, we can see that the absolute minimum, or infimum of it, is 3, which is the same as the square root of 9. This probably looks pretty trivial, but this step is perhaps the most important part of our research and of this presentation. Doing some very simple but important algebraic manipulation, we can rewrite the length of a side of a triangle, in this case A, as an infimum using the geometric mean. The other reason for using infimum and supremum is with the square root of a squared plus b squared. It has been shown that this square root is equal to the supremum of the function f of x is equal to a cosine x plus b sine of x. Yet, again, I don't have time for an extensive proof. So why not another example? In this case, we have the square root of 25, which is just 5. Knowing my Pythagorean triples, I can rewrite 25 as the sum of 3 squared plus 4 squared. Using our new supremum, we can graph the function and see that the absolute max, or supremum, is 5, which is equal to the square root of 25. Now, through some nifty math magic or algebra, we can derive the equation I had shown a long time ago from the Pythagorean theorem we have all come to know and love. What is interesting and important to note here is that the square roots are gone. Now, if you don't trust me and believe what we have is true, How about an example to show you otherwise? Going back to the navigation problem we did at the start of this presentation, we can use our new equation to calculate c again, which should be 2.5. To start us off, we plug in our a and b, or the lengths of a and b street, and simplify a bit to obtain the supremum. Instead of dealing with the supremums directly, let us deal with the infimums first. Graphing the two functions inside the infimums, we find the first infimum to be 2 and the second infimum to be 1.5, which makes sense when looking at how we derive these infimums in the first place. Now then, we take these values and plug them into the supremum and obtain a new function. Graphing the function, we are able to see that the absolute max, or supremum, of the function is 2.5, which is the same as the c we calculated a long while back. Of course, this took a little more effort to calculate the answer than how we did it before, but there is merit to this new equation. I may be showing off a little with this, but here's the more advanced version of the equation we have derived previously. Yet again, no square roots to be seen. This lack of square roots makes our equation stronger and better than the previous Pythagorean theorem, because our equation holds in more general settings where the old Pythagorean theorem will most likely fail. Now, like Pythagoras, we don't know what future applications this new equation could be used for. That's just the nature of pure math research. What I can tell you, though, to end on a positive note, is that someday in the future, some mathematician will stumble upon this and find a real application that can impact our lives for the better, just like what has happened for Pythagoras and his theorem. Thank you.